Okay, so let's start. So, in previous classes, we mostly looked at the introduction to machine learning, then signal processing, and some Python programming. So today we can start something, uh, uh, something one step more towards machine learning, that is signal representation. Yeah, so just one small kind of uh, yeah, so just a small precursor. So how do we represent mathematical data, be it numbers or integers, floats? We generally use some representation like tensors. What is a tensor? The name looks new to us, but actually we have all studied it before. So zero order tensor means a scalar. Scalar means just a variable x which can take a scalar value. It can be an integer or a float. Float means a decimal number, a real number. With precision, you cannot have infinite precision. So that is a scalar. Then what are the examples of scalars? If you represent temperature at a particular time, that is one scalar. Time, frequency, amplitude, phase, all these are scalars. Then first order tensors, they are vectors. So you have seen vectors. So if we have a set of time values, a set of time points, that is one vector. If I have a set of frequencies at different times, let us say, that is one vector. A set of amplitudes could be one vector. A set of phases could be one vector. So you have seen vector representations before. Similarly, if you have a point in three-dimensional space, that will be one vector. So these are all vectors. You have seen this vector h, which is a discrete time series, represent time series. So now this is an important thing. You will realize it little later. Indexed with one index. So when I say a vector, if I call it as, let's say, f, then it can be indexed with one index only. F0 has one value, F1 has one value, F2 has one value, like that. So this will be more, you'll be able to appreciate this more in the next slide. Matrix. So a second order tensor is a matrix because we need two indices to get to one value, to get to a value, which means if I have, let us say, this matrix, which is visible here, I need to get to this value, I need to specify two numbers. Let's say in this case x 0, 0. If this is x, then I will say x 0, 0 is the value 2, x 0, 1 is the value 7, and so on. So I need two indices to represent a second order tensor, which is also a matrix. What are the practical examples of this? We saw spectrograms in the last class, like when you take spectrum with short time windows, then you can form a spectrogram in which the y-axis represents the frequencies, the x-axis represents the time. Basically the time windows as they are progressing. So these are second order tensors. Then third order tensor. What could be a third order tensor? Can anybody give an example of third order tensor? Color? Image. A colored image. Very good. So what is a colored image? So each image, if you look at a grayscale image, each image is a point with value between, let's say, 0 and 1. If it is 0, you call it black. If it is 1, you call it white. But if you have a colored image, it has got three channels. What does that mean? Red, green, blue. So the red channel will have some value between 0 to 1 or 0 to 255. Similarly, blue channel will have something, green channel will have something. So you have 3 channels. So basically you have got 3 matrices, and that forms a 3-dimensional tensor. Because to access a value in that, let me draw something so that I make myself more clear. So an RGB means red, green, blue. Now to access a value, if I want to know what is the value of this pixel, or what is the value of at 0, 0 in the red channel, what is the value of 0, 0 in the green channel or in the blue channel. So you need 3 indices. One is the M, N, and the channel C. Okay, so that's a colored image. Similarly, a collection of matrices or a collection of spectrograms or a collection of grayscale images, that could also form a 3-dimensional matrix. For example, a black and white video, right? To access each one value, you will need to specify first what is the location in that matrix, and importantly, at what time instance is that matrix occurring. So you need 3 indices to get to the value. So that is a 3-dimensional or third order tensor, or it's also called a block. Let's come to higher order tensors. Let us say a 4th order tensor. Can anybody give an example of a 4th order tensor? Yeah, thank you. I was expecting this answer. A colored video, that is the 4-dimensional 4th order tensor, because you have each block of RGB image, and then the 4th dimension is the time. So in this way, you can have nth order tensors. So if you try to visualize it, it will be difficult, right? But if you can visualize it like this, you can just say this is x, I, j, k, or so on up to index n, then it is an nth order tensor, right? Okay, this was, I think, simple. Now let's come to something more interesting. Okay, so to be able to talk about machine learning, to be able to talk about data, to be able to talk about classes, to be able to talk about prediction of something, you need to have a notion of distance. How do you differentiate 2 things? So what do you do in machine learning? Give me some examples. One is image recognition. Let's say I am able to see somebody's image and I can say, oh, this is Ravi. I can see this is Swati. Because I'm able to distinguish between the 2. So I have a notion of difference, a notion of distinction, which is very important. Okay. Mathematically, what is the notion of distance or difference we have? A very common notion which you have been studying since your high school days is L2 norm, or Euclidean distance, or Cartesian distance, so many names. So this is basically, you get the vector and then you take the difference, so element-wise difference, square element-wise, and then add all the elements, and then take the under root. That is your Euclidean distance between 2 vectors or 2 matrices or whatever. Just take 2 objects of the same size and take the difference and find the L2 norm of that, and that is it. So let us say in this example, so for example, in the Cartesian space, in 3-dimensional Cartesian space, you can have 2 points, x1 and x2, and you can find the distance between them. That's also the shortest distance between them, right? So it is given by the Euclidean distance, or L2 norm. And then for this example, if I calculate the L2 norm, it comes out to be this. Okay. Another notion of distance. Now our points may differ from each other, not in magnitude but in direction, right? Any examples? Any examples of this? Okay, it's fine. Huh? My position, yeah, basically, when they will look towards me, so my direction basically, right? That is not dependent on the distance because it is more or less same, but the direction is important. So how do we measure the distance between two entities in direction? So that can be measured by cos theta. If you know the angle difference between the two, take the cosine of that angle. If two objects are exactly same in the same direction, then cos 0 will be 1. So this is similarity measure. So maximum similarity, and if they are in opposite directions, then the similarity is cos is -1, right? So the least similarity. So this, how do you implement this? Basically, you take the vectors x1 and x2, you divide them by their norms, L2 norms, and then take their dot product, and that is the cosine similarity. This is very useful. We'll see some very good applications of cosine similarity measure. Okay, and sometimes you have vectors which are not L2 normalized but L1 normalized. A very popular example of that is probability distribution, PDF, when they are non-negative, of course. So how do you measure difference between them? How do you measure the distance between them? There are some popular measures like KL divergence. What is KL divergence? So the formula is given in front of you. You have two probability distributions, P1 and P2. What does that mean? It means that they are non-negative, and their sum is equal to 1. So unit sum and non-negativity. These two things define P1 as well as P2. Example is given here. And then when you find the KL divergence between the two, you get some measure. And this measure is always positive, and it increases as they become more and more different. Right? And it is 0 when they are exactly same. You can verify if P1 is equal to P2, what will happen? Log of P1 upon P2 will become log of 1, which is 0, and that's how you get zero divergence, which means they are the same distributions. Okay, we discussed some mathematical notions of similarity or distinction, but does it really work? Okay, I have an audio for you. Maybe I have to go back to this thing. I have to use my microphone. Okay, and the second one is, what's the difference? Could you hear it at the back? What was the difference in the two sounds? What was the difference in the two sounds? I'll play them again. Yeah, they're same. There is no difference. Same frequency, same amplitude, everything is same. No difference between the two sounds. But if you look at their vectors or their representation, what is the difference? Okay, you call it phase, but if you take a difference, if you take a Euclidean distance between the two, the Euclidean distance comes out to be 19.9. So just the difference between these two, the L2 norm of the difference is 19.9. It's a huge value. But just now you listened to it and there was no difference, right? So this means that L2 norm does not capture what we want to capture. Are X1 and X2, no, these are some signals, audio signals which I just played. Okay. Huh? Yes. We are taking the difference, squaring them up and adding it and under root. The Euclidean distance. Huh? Euclidean distance we just discussed, right? In this case, you take for each value of n, you find out x1 and x2, take the difference, square it up, sum all these differences, and then take the under root. It is already discrete. It's already discrete. It's just drawn very closely. Maybe that's why it's not visible. But it is.
Depend upon how we discretize it, how we know the value.
But the signals are different, right? They are completely out of phase.
No, what I'm saying is the value of L2 norm would depend upon how you discretize it. What's the fineness of the discretize?
Yeah, fine. Good point. So what we generally do is, okay, good that you brought up this point. Let me write it down here too. So what we do generally is, let's say x1n minus x2n, and you take this Euclidean distance, basically, okay, sum over n equal to 0 to capital N minus 1, square it up, and then take the under root. So what you can also do is, you can divide it by capital N. Does that make sense? So you're kind of normalizing it over the length. So basically if I take too long a signal, the Euclidean distance will keep on increasing, but I don't want to do that. I want to keep it, I want to find a generic measure which can measure the difference, and even if I take longer signal of same kind, it should not keep on increasing, so I normalize it with the length of the signal, right? Okay, so this is how we see that the distance measures which are mathematically very popular may not make sense for our perceptual tasks or our actual tasks which we want to do. I will show you another example which you might be able to relate to better. Okay, so what is the digit, or what is there on the left image? A digit 2. On the right image, what is the difference? What is the difference? So if I am doing a digit recognition task, what is the difference? Huh? A digit recognition task. Huh? Does not? There is no difference. Very good. But if you find the Euclidean distance, how much is the Euclidean distance? Under root 10. So you take element-wise difference, square it up, add them up, and then so you get root 10. So this means the Euclidean distance is not a nice measure for a visual task as well. So like that, can you tell me more tasks where our normal Euclidean distance or our normal cosine similarity or KL divergence or other measures may not make sense? Practically, most of the tasks, they don't make sense. I gave you example of speech, I gave you example of image. You take example of, let's say, in text, you want to see whether these two emails, okay, we took the example of junk email, a spam email. If the two emails are, an email is spam or not, another email is spam or not. Let us say we want to find distance between two emails. You take two junk emails and representing, means how you represent that is up to you. Maybe you can represent each word with a number, take their Euclidean distance, and the distance will not be 0, even if both are junk emails or if both are genuine emails, right? The difference will not be 0. So this means that the Euclidean distance is not, in its raw form, is not applicable. So where are we doing mistake? Okay, it becomes more complicated. So you can have same person and viewed from different angles, and or same person on different days in different dresses, and Euclidean distance will not make sense at all, right? Then how do you do it? So what is lacking here? So what is lacking is space. So you have not defined the space properly. You're trying to fit everything into Euclidean space or a spherical space, like a surface of a sphere, because cosine similarity measure is a measure for a spherical or hypersphere. Similarly, KL divergence is a measure for, technically it is called a simplex. Basically, when all elements are non-negative and their sum is equal to 1, that forms a simplex. So KL divergence is a measure on the simplex. And then you are trying to force your data, force your whatever you want on some standard space, which is simply not correct. Then how do we do it? So let us first understand what is space. Space provides support and a distinct identity to every object. So what is the object in this case? We saw, let us say, sounds. Close your eyes and listen to different sounds. You can make a distinction between them, right? Similarly, we looked at the example of images. Same person, different images. So what is distinguishing two different persons, the images of two different persons? There is a notion of space. That space provides support and a distinct identity to every object, a unique identity to every, because of which we can identify that thing as separate or different from other things. That is the notion of space. Very important. So what you have seen, or what we generally see in mathematics, we have seen examples of Cartesian space, Riemannian space, spherical space, space, and in this way we have seen more and more complicated geometries, but that is not what will serve the purpose here. What will serve the purpose is you have to define a new space. Okay, so I have given here more examples of space because you will be working in different areas. Somebody will be working in power systems, somebody in aerodynamics, or somebody in chemical, dealing with chemicals. So let us understand the notion of space first. What is space? So space is not just empty space. You ask what is space, people say vacuum. What is space? Vacuum. No, vacuum is not space. We talk about Cartesian space, Riemannian space. Similarly, you can have many kinds of spaces, but where is this notion coming from? This notion is coming from perception. When you eat food, you are able to distinguish between an apple and a banana, even without looking, just from the taste. Why are you able to do that? Because you have got a taste space. In the space of your taste, you can clearly identify this is apple, this is banana, this is potato, this is I don't know, something. So this is the taste space. Then sounds you listen to. You close your eyes, just listen to sounds, and you can distinguish who is speaking. Is this Amitabh Bachchan speaking, or is this Sachin Tendulkar speaking? Or if you are fond of music, which note it is? Is it somebody is singing sa or re? Somebody singing this rag or that rag? Or somebody is playing a flute or a violin or vocals? Similarly, you can, just by hearing, you can distinguish between English or Punjabi or Marathi or Telugu, whatever language. You can distinguish just from sound. Why? Because in all of these cases, there are different spaces which you have learned, which you identify, which you are associated with. Let's see some more examples. Images you see. What do you see? You see colors, red versus green versus blue versus black. These are all different objects which are lying in your visual space. Then you also see different entities like marigolds, jasmines, roses, or different kinds of flowers, or different table, chair, desk, classroom. All these lie in your visual space. You identify or distinguish them based on your visual perception. Then the scents you smell. You smell something and then you can tell, oh, I can see I'm in this place. Some people can do that. Okay. And then whether this is sandalwood or this is saffron, or this is even the foods you can distinguish based on smell. This is yogurt or milk. You can distinguish based on smell. Similarly, you have got touch experiences. You can distinguish whether something is cotton or brick, hard surface, soft surface. Just from touch, you can people who do not have visual modality, just by touch they can tell who you are. Because they have developed, very important, they have developed their tactile space, their touch space. That just by touch they can distinguish, they can identify. So spaces are not fixed. You can learn them, you can, based on your association and your experience. And then hot versus cold. You can distinguish because you know that space. So this is the notion of space, which is very deep, but here we are interested in something else. We are interested in giving this notion of space to a machine. How do we do that? The kind of spaces we discussed just before, that was based on human perception or our sense perception. But how do we make the machines understand this notion of space? How can machines distinguish between hot versus cold, or roses versus jasmines, or apple versus banana, or flute versus violin, or a speech in English versus a speech in Marathi, or so many examples which we discussed. So how do we do that? So the question is very old, and the answers are still new, and answers are still unsolved. I mean, these are unsolved problems. So one popular approach which we take up in science is find detectors or find sensors that correlate well with our experience. Does that make sense? So for example, I hear some sound. What detector can I use that I can that correlates with what sound it is? A vibrating membrane. Somebody discovered, maybe Edison it was. Edison discovered, okay, if there is a vibrating membrane, it correlates with what we hear. There is some sound. If you place the membrane properly, it will vibrate. And then they thought, okay, can we make something to record those values so that we can capture this auditory experience? And that's how Edison came up with gramophone. So that was about sound. What about images or the visual perception? So somebody found, okay, there are some chemicals like silver nitride. What was it? Silver sulfide, I think. Nitride. Okay, it forms sulfide and then it gets the different color. Okay, I have to check that. So somebody found that there are chemicals which correlate with colors, or with which in the beginning it was not colors. In the beginning it was light. If you expose something to light for some time, it changes color, and if the unexposed part does not change color. And using that, they thought, okay, this correlates with my visual perception. Can I use it to capture the visual perception better? So they came up with cameras, Polaroid cameras. Then, okay, let's go further ahead. So somebody said, okay, there are certain metals which expand when they are heated and they contract when they are cooled. Basically, they correlate with our touch sensation or our touch experience of what we call as temperature. Temperature is one aspect of our touch experience. And similarly, another aspect of our touch experience is pressure, how hard I hit you or how soft I touch you. So people discovered that there are crystals which can respond to different kinds of pressures. So they used those crystals to form piezoelectric crystals. Basically, if you press them, they will show some potential difference, and that can be recorded and measured. Measured and recorded and saved for further use. Okay. Fine. So now where we have reached. So we have found some nice detectors or nice sensors which correlate with some of the perceptions or experiences which we have, right? But they are not enough. Just the raw readings are not enough. I just now showed you raw reading of a microphone recording different sounds. Same sound, but different recordings. So just by looking at the recording, the sensor reading is not enough. So what we need to do, we need to formulate the space. in which the things which we are interested in, they are separated, and the things which we are not interested in are not separated, right? We need to formulate a mathematical space that correlates with what we experience or what we are interested in. Okay, so technically that is called feature extraction. So what is feature extraction? So first, you identify what you are interested in. For example, if you want to distinguish between different instruments, let's say flute versus violin, then you are not interested in what melodies they are playing. You are interested in their identity, not the melodies. You are not interested in how loud or how soft they are playing, but you are interested in their identity, right? So you are, but another person might be interested in listening to the melody, which raga that whoever is playing, whether it is flute or violin or a human being singing. I don't care. I just want to know which raga it is. Then I need a very different representation of space, a very different kind of features, right? Similarly, in images, if I am interested in knowing who is sitting, the person recognition kind of task, then I need different kinds of features. But let us say if I want to count how many people are sitting, a different kind of space is required. Let us say if I don't want to identify people, I don't want to count people, but I want to find if anything suspicious is happening, or anomaly detection, something anomalous is happening, then I need a very different kind of space. A very different kind of features are required. So we identify what we are interested in, then we identify which detectors correlate with it. Means you need a camera, or you need a microphone, or you need a sonar sensor, or you need a voltmeter, an ammeter, or you need pressure sensors. So you find out the detectors which correlate with what you need. And then the third task is that you design space, the features which will correlate with what you are interested in, right? Next. Now, okay, assuming that we have found the good sensors or good detectors, now the next task is how do I form features which will distinguish between what I am interested in. So the features, their characteristics are, they should be distinguishing for what we are interested in. They should distinguish what I am interested in. For example, you want to identify spam email versus non-spam email. You have to find features from the text which will be correlated with that information, right? And they should be invariant to what we are not interested in. Like in spam email example, I am interested in maybe keywords. Certain keywords, they might be a good feature to distinguish between spam emails. But what may not be good features, I don't want to know whether the person is writing a long email or short email, or whether the person is addressing me or addressing somebody general, whether the person is writing in English or writing in Hindi or some other language. So there can be different dimensions which I am not interested in. So I would like my features to be invariant to those dimensions. I'll give an example of audio because audio is very rich. The same example of music. Many instruments are playing and you have notes playing. If I'm interested in notes, then I will not look at the entire signal. What I am interested in, I'll be just looking at the fundamental frequency or the pitch. We looked at the pitch, right? We discussed about pitch or the from spectrum you identify the fundamental frequency, and I'm interested in that. That is my feature. But let us say I want to know what the person is singing. What words, what lyrics the person is singing. Then those notes or those fundamental frequencies are of no use to me. I have to look at some other features which will correlate well with the content, the linguistic content of the sound, right? So I have to look at I have to extract features in a different way. Okay, so important. They should be distinguishing for what we are interested in, and they should be invariant to or non-distinguishing for what we are not interested in. And third, very important, minimal in size. I don't want to overload my processor. I don't want to overload my memory. So what I want, these features should be as small as possible, minimal in size, so that they are easy to store. Like small in size means I can store very effectively, and they are very easy to process, computationally very fast, right? So I'll give you an example. How many of you have listened to wave files, wave format? How many of you have listened to MP3 format? Okay, I'm sure everybody. So just to wake you up. What is the difference between the two? Wave format and MP3 format? Huh? Yeah, compression. What is the meaning of compression now? The same thing. So from the raw audio, wave format is the raw format. It's the raw audio. Just the waveform is saved there. Wave. That's why it's called wave. But if you want to save it, it is very large in size. So can we do something smart? So people, they found out, okay, what our ears are sensitive to. Our ears are not sensitive to phase. Our ears are not sensitive to so many things in the audio. So just extract certain things which we are actually sensitive to. They found out, they tried to find out what is the fundamental frequency, what are the prominent bands in the spectrum which we are sensitive to, and just playing on that, they can compress the audio so much. Okay, so that is a kind of feature extraction with a different goal. The goal is to reproduce the signal again without any perceptual distortion. Okay, so I am giving audio examples today, so let's continue on that line. Tomorrow I will give, day after tomorrow I'll give examples from images too. Okay, let's look at audio. So let's start from the same thing. We'll see how do we extract features for audio. So Edison invented gramophone, or this instrument to record sounds and then play back sounds. So this is how a typical audio. This is how a typical audio waveform looks like. So this is the time dimension, and this is how the membrane is vibrating. I'll show you on the next slide. So we found that when there is sound, the membrane of the microphone means first we saw that membrane vibrates, then we put it on the microphone and saw, okay, can we use it? So the sound makes the membrane vibrate. How to store the signal now? In electric form. So how do we? Because we are very good in storing anything in electric form. We have hard disks and computers. Convert physical motion into electric signal. How do we do that? How do we convert physical motion into electric signal? Transducers, very good. This is how a transducer may look like. So you know from the Maxwell's equation, what is it called? Whenever a charge moves in a magnet, you get. Whenever a charge moves in magnet, it experiences a force. Whenever there is a motion, whenever there is a motion in a magnet, or when a conductor moves in a magnet, what happens? The electrons will experience a force, and they will create a potential difference. And you can measure the potential difference. So that is what is happening in this figure. So you have sound in. So when the sound comes in, this is the diaphragm or the membrane which vibrates. As it vibrates, there is a fixed magnet here. And when this membrane has some coils wrapped around it. So when it moves, the coils also move. And when the coils move, what is generated? Electric current is generated. And that is what is measured as signal out. And this can be extracted and then amplified using amplifiers and then saved in hard disks. First you have to, what do you do? You have to sample and quantize. By sampling and quantizing, then you will get numbers which you can save in your computer. Generally, that device which is used for sampling and quantizing, that is called ADC, analog to digital converter, or in common language it's called a DAC card, DAC DAC card. Another way to convert motion into signals, electric signals, is like this. You have a condenser or a capacitor. In a capacitor, the capacitance depends upon the distance between the two plates, or so these plates are connected with the membrane, and when the membrane vibrates, the condenser plate also moves. The distance changes, the capacitance changes, and that's how you get signal. Means the change in signal you measure using your amplifiers and then save it in your computer. Okay, so this is how we record. Generally, how we do, you are speaking or singing, and then microphone does that for you, and then you get the signal, you save it in your computer. Okay, now questions about what should be the sampling rate. We have been looking at this question for some time in the past. How do we know what should be the sampling rate? How will you determine the sampling rate? Yes, it must be at least it must be greater than at least twice the maximum frequency of the signal, right? So now the question is, what is the maximum frequency the signal will have? Signal can have any frequency, right? But there is a limit on what frequency we can hear. Signal can have any frequency, but we have a limitation. We cannot hear all the frequencies. So that's why humans generally hear in the range 20 Hertz, 20 kilohertz, which means effectively any frequency above 20 kilohertz can be compromised. It can be given up. That's why popular sampling rates are, if you look at commercial CD recordings, they generally have 44.1 kilohertz. So this trend was started by Sony, and it is still continuing. 44.1 kilohertz for CD recordings, and it is considered a high quality sound. You can go to further higher frequencies as well, but this is 44.1 is mostly sufficient. And then people also use 16,000 hertz or 22,000 hertz. Those are also popular numbers. But then you are losing some high frequency informations. Okay, then there is quantization. So first you had sampling, then you can have quantization. You convert the number to a digital number, convert the real number into a digital number, basically with some precision. So let us say you want to save the number. Why do we do quantization? To save the number in some memory location, right? Let us say you have got 16 bits. What does that mean? You have got 16 zeros or ones. So you have got 16 placeholders, like that, 16 bits. And each one can contain either a 0 or a 1. Right? So how many numbers you can save? 2 to the power 16, because each placeholder can hold 16 numbers. This means that you can only have these many integers or these many values. So in your waveform, when you want to save your values, you can choose what values you want so that you can save them effectively. We can discuss this little later. Now we don't have that background because we need some probability theory for that, which we have not studied yet. Okay. So finally, audio is a stream of numbers. We represent it as a vector of shape n, 1, where n is the number of samples. Okay. Then there are different attributes in your signal which you want to look at. You remember what is the goal? What's the goal which we are working towards? The goal is to find feature representation or do feature extraction. And we want to see what are the good features for my data, for the task which I am interested in. Let us see this. So this was an audio file with frequencies varying from 200 hertz to 15,000 hertz. So you could hear some of them in the beginning very clearly, but as it goes to higher and higher frequencies, it becomes more and more difficult to hear them, right? So what is this quality of music, or what is this attribute of sound which you are able to experience? You're able to distinguish between these different notes based on what? They have same amplitude, they have got same sampling rate, everything same, but what is different? That is called pitch. Don't worry about how I generated that signal, but if you hear those different attributes, then you can distinguish between them because of your pitch space. It is a subspace of your auditory space where you distinguish between notes of different quality. That is what this attribute is called, pitch. It's a perceptual attribute of sound. So musical notes, for example, they correlate with this property. Now, how do we bring it to real machine, or how do we quantify it? So we generally find that if you have the waveform, you find the F naught, or the fundamental frequency, or the frequency of, like, you remember the smallest cell you take and see how many times it is repeating in 1 second. That is the fundamental frequency. And then it is found that as you change the F naught, you get you get to hear different pitch values. So F naught correlates very well with pitch, but not linearly. It is not that F naught is pitch. F naught is a measure which is found in mathematics, and pitch is a quality which is found in real perception. They are not one-to-one correlated, and in many cases they are not correlated also, but those cases are little far. Let us discuss simple cases for now. So generally they are related in a non-linear way. So people did some experiments, some psychoacoustic experiments, and they tried to find out, okay, what should be the value of pitch so that you perceive double the frequency. Musicians generally are good with identifying frequencies because they work with musical notes, right? So based on the experimentation, it was found that, okay, these curves fit very well to the experimental data. So they call it as a MEL scale. It's like a logarithmic scale. It's called a MEL scale. Slightly different from logarithmic scale. Okay. Then generally in music, people don't use the entire range of 20 hertz, 20 kilohertz. They use, let's say, 30 hertz to 4 kilohertz. Another important thing to understand space. Remember, we are talking about space. How to formulate this pitch space. This pitch space, we found out, okay, it can be formed using F naught values. It can be formed using a nonlinear scaling. But then what about resolution? How close frequencies we can distinguish? How close the two frequencies could be? If I give you one frequency of 100 hertz, another frequency of 100.00001 hertz, can you distinguish? Of course not. If I give you 100 hertz versus 200 hertz, can you distinguish? Yes. So what can be the smallest distance which is still perceptually you can perceive? That is called the resolution. So the resolution is also different for different F naught values. These will be helpful for us to formulate our pitch. How resolution will be helpful? In deciding the quantization, right? Okay, let's look at another attribute of sound which is called loudness. If I'm speaking very loud, or I'm speaking quietly, or means very mumbling something. So that is the perceptual quality, perceptual attribute of sound that is related to quiet versus loud. So it is called the loudness. So there is a way to quantify it. We compare the amplitude of the waveform, or the square of amplitude, or the power of the waveform with some standard value, and we say what is the ratio, and we calculate it using decibel scale. That means, okay, let me write it down. So if you have some value P divided by P naught, you take a log, and 20 times log of this, log to the base 10 basically. This is a measure of loudness. So P is the power, P is the energy in the in the sound which you are interested in. P naught is the baseline or the base energy, then which is generally taken to be like atmospheric pressure. And then that is how you quantify loudness. I'm not going into details because we are not we won't be dealing with it much, but there's a reference you can read on Wikipedia if you want to know the details. Then again the range. So somebody may say, yes, loudness is exactly related with the pressure level. The answer is no. It is not exactly related. This is also a nonlinear relation, as you can see. So every red line is on the y-axis is the sound perception level, and the x-axis is that we perceive them as same at different means at a smaller frequency I perceive this is loud, and at a higher frequency I perceive this is equally loud, right? And but that pressure value is not the same. Am I making sense here? Am I going too fast? So what I mean to say is, let us say I took a sound at 100 hertz, I took another sound at 10,000 hertz. Now I change their amplitude levels or their pressure levels, and I see when do I perceive them to be exactly same pressure levels or same loudness. And perceptually I do this experiment and I fix those values, and then I look at the value of pressure of this sound, look at the value of pressure at this sound and plot it here, because these two are same loudness perceptually. So that's how I get one red curve. Okay. Loudness versus pitch. So if you are in this range, if at this frequency you perceive these sounds as pleasing, these sounds you don't hear, and over these sounds they are painful to listen to. Then another perceptual quality of sound is timbre. So people pronounce it in different ways, timbre, or I call it as timbre. Say. So what is timbre? Anything which is not loudness and pitch, they try to group it as timbre. So what does it actually mean? It correlates with the source of sound. If it is coming from flute, it is a different timbre. If it is coming from piano, it is different timbre. So in this way, but what exactly it is, so that is very vaguely defined. Mathematically, how do you do it? People use all different kinds of properties extracted from the waveform given on the figure you can see. But we will be using machine learning techniques to extract this information. Let me just finish. There are only 2 slides left. Binaural hearing. Then we have got 2 ears. So with 2 ears, what we can do is we can find out different directions where the sound is coming from based on interaural time difference. Sound which is coming from this direction will reach this ear first and this ear later. And then interaural intensity difference, the sound which reaches here will be larger in intensity than this sound because it has to cover so many other obstacles on the way. And then what are the uses? The uses is in microphone arrays for source localization, for source separation, 3D sound effects. So these are the uses of microphone arrays. Next one is some practical thing. I need to spend a little more time here to be clear. So there are just 2 slides. We'll do it next time. Thank you.
Let's start. Good evening. Last time we were discussing about that we use some detectors or sensors to read the data or different kinds of signals, but we cannot use those signals in their raw format. The raw signals we cannot use for processing because we saw some examples. Okay, you cannot just take raw samples and if you just find their Euclidean distance, it is not giving you a meaningful space. So you need to construct your space carefully based on what you are interested in. If you are interested in, we took an example of audio. If you are interested in distinguishing between different instruments, then you will construct your space differently. You will look at different kinds of properties of the signal. If you are interested in music classification, basically different notes playing, then you will construct different kind of space with a different kind of distance metric. And if you are interested in the linguistic content, you will look at different kind of representation, right? So in essence, what we discussed was you have to construct a space which is meaningful for your task, and then you have to construct which has desired distance properties, which will similar things are grouped together and dissimilar things are separated out, right? That was the essence. Now we looked at some examples from sounds, different kinds of sounds, how they are represented. So let's go through the part which we had to rush through in the last class. So we compare sounds using phase invariant representations. I played two sounds which were the same sound, but the phase was opposite. So we deduced that if we want to compare these two signals, then let us first ignore the phase part, or let us construct a representation which is invariant of phase. Then we looked at the pitch properties. We found that we do not hear all pitches equally. And also we found that the range of variations in pitch is different. Let's say I mostly will hear pitches in the range, let's say 20 hertz to 4000 hertz. Above that is very rare. So it is meaningful to use a logarithmic scale where pitches are, means the lower pitches are finely separated and the higher pitches are coarsely separated, means their resolution is smaller, right? Is this point clear? No? So what I mean to say is, that you have pitch values. Let's say this is 100 hertz, 200 hertz. In this way I can keep going up, and after let's say 4000 hertz, the distances don't matter. So what I can do is I can use a logarithmic scale where 100 and 200 are finely separated, but as you go up, the distances are becoming smaller and smaller, which means that I'm giving more weightage to this frequency range, means that they are finely separated. Okay. Then compare magnitudes on the log scale. So we found that if you look at the spectrum, maybe I have some good spectrum here to show. Let's look at this spectrum. So the kind of variation will be like this. If I plot the spectrum, it will be like this. Means the smaller frequencies will have very large amplitude, and the larger frequencies will have very, very small amplitudes. So the dynamic range is so large. This dynamic range is so large that it is meaningful to use a logarithmic scale to reduce the dynamic range. Means if one number is 10,000, the other number is 1,000, next number is 10, next number is 1, next number is 0.1. So how do you form meaningful features, right? When you will do comparison, let's say Euclidean distance, then the one with a very large magnitude, let's say 10,000, definitely it will get weightage, right? Because 10,000 minus 9,000 is a huge number. On the other hand, 0.1 minus 0.09, nothing in front of that, right? So to make a meaningful distance metric, you kind of bring them to the same dynamic range. And this you do with the help of a logarithmic scale. And then compare spectra on Mel-like frequency scale. We discussed, okay, this point again, that the pitch values or the higher frequencies are not, we don't have finer resolution at those frequencies. Okay, so some examples which may be helpful here. So here I am speaking the same sound. The word here is Hari. And if you say Hari, if you say, these are two different utterances. Maybe I will show you the utterances also. Okay, let me use the microphone. Yes, this is the.
Hari.
Is it audible? Oh.
Hari. Hari.
Sorry.
Hari.
And this one.
Hari.
Like they sound completely different, very different, but the linguistic content is same. So that's why if you look at this representation, they look very similar. On the other hand, this is a word called hara.
Hara. Hare.
Yeah, and you look at the representations, they are completely different. So Hari versus Hari and Hari versus Hara and Hari versus Hare. So if you look at the representation, they are different. So this is the representation which is used generally to represent phonemes, means speech recognition. So look at the tricks which are used here. One is that the frequency scale, the y-axis, which is hertz. So it is in hertz, but it is a logarithmic scale or a Mel scale to be more precise. And if you look at the values, they are also on a logarithmic scale, so that the dynamic range is almost similar, as you can see in the figures. That's why you see similar colors. So yellow means a high value, blue or black means a low value, and everything throughout the spectrum it is close to yellow, which means they are high values, similar values. Okay, so this was the example to show. Okay, this is an interesting example. Let me play this to you.
A, I, U, E, O.
So these are different vowels, and you can see their representations look okay. It's not very clear here, but they actually look different. If I plot it in some different ways, they will look very different. So the different vowels. So what is same? If you look at this frequency, the peaks, they are almost occurring at the same position, right? But what is different is the distribution of energy over the different peaks. So if this is f0, this is 2f0, 3f0, 4f0, so different frequencies. Of course, this is logarithmic scale, so if you go higher, the distance becomes smaller. But what is different is the distribution of energy over these peaks. If this vowel is very different from this vowel, and this is very clearly visible in the distribution of energy across different peaks. So that's why this is a meaningful representation. Okay, so why this exercise? So we went through this exercise to emphasize this point that features have to be represented very carefully based on what we are interested in. If I am interested in some content, then I can carefully choose my features to show that, to represent that. Okay, as a side note, as a matter of fact, these days there is a trend to automatically extract the features with the help of machine learning. So they take very raw audio, let's say waveform, and try to extract features from the raw waveforms of any signal. That is one trend. But even to do that, they have to use tricks to take care of so many things, like the phase shift. We saw phase shift. So even if they want to extract signal features from the raw signal, they have to take care of the phase shift and so many other things. So basically, signal processing is so very important in designing your features carefully. Okay, next. Let's come to another class of examples. So this is from visual perception. So visually, we can form all colors using three basic colors: red, green, and blue. Red, green, and blue lights combine in equal proportions, they form white color. And if they are in different proportions, they can present different shades, as is visible in the first, the top figure. And so whatever images we see, let's say here is an image of a rose plant. So this is actually represented in our device in three channels: red, green, and blue. So basically, if this is a representation, it consists of three matrices: the red matrix, the green matrix, and the blue matrix. And each matrix contains values between 0 to 1 or 0 to 255, because it is 256. Okay, it's 2 to the power 8, I think, yeah, 8-bit representation. So 2 to the power 8 values it can take. So if you normalize it between 0 to 1, so you get, so basically it is each pixel, each point can take a value between 0 to 1. And if it is close to 0, you see it as black. If it is a large value, you see a bright color. So this image is a combination of these three channels: red, green, and blue. And if you look at this figure, you can see the red rose is mostly bright here in the red channel, and here it is dark in the green channel, here it is dark in the blue channel. And you look at the leaves, they are very bright in the green channel and very much less bright in the other channels, red and blue. So okay, next. So now, how do we design features for image recognition? So here also, useful things are, we are very sensitive to edges, corners, edges, blobs. Blobs means like small dots. Corners. So all these things we are very sensitive to. Means our eyes are very sensitive to these things. So now you have to remember that when we are trying to formulate our space, the basic space comes from us, right? We are trying to mimic human space in the machine, right? Because we want to mimic how we see things, how we hear things, how we touch things. So that's why it is important to take lessons from human visual system or human auditory system. So that's why we are looking, so our eyes are sensitive to changes, these kind of changes. So that's why we are also interested in representing these changes in the images. If you want to compress an image with minimal information, then these are the informations which you must preserve. So that's what JPEG does, right? JPEG is a format of images which compresses the image from a large size to a smaller size. And how they do it? They use these features, which our eyes are actually sensitive to. And they try to ignore the features which we are not very sensitive to, right? Okay, now here is a nice concept of filtering. So what is this concept? This concept is like this. I want to detect edges, right? How do I detect edges? So one very simple way is, okay, on the left you can see a black and white image. This is a representation of a black and white image. All zeros, you can say these are black. All ones, they are white. So it's like a blackboard on which you have written something with the chalk. The background is black and the foreground is white. And you have this filter. So okay, what I want to detect now, I want to detect edges. Let's say the horizontal edges, means I want to detect these things, these edges, this is one edge, this whole thing is one edge. So I want my output to be such that these edges are highlighted and everything else is just ignored. So if I apply this kind of filter, what does it do? It will take this row and the row on top of it and subtract the two. It's like a differential operator, right? You take a difference, and if the difference is non-zero, this means an edge is present there. If the difference is 0, this means edge is not present, or horizontal edge is not present there. So that's what I see in the figure now. So there are 6 columns here, and here we have 7 columns. Why? Okay, so first of all, what is this operation? What is this operation? Convolution. Anybody else? Convolution. Anybody else? Yeah, elementary multiplication is there, that's true. But, okay, how do you achieve it over the entire image? So, okay, let me go into some details. So I will take these 4. I'll do element-wise multiplication with these 4, and then I will sum them up. I will get a 0, and this is here you see a 0. Let's see some other value. Here is an edge. Oops. So I will take these 4, and I will subtract. I will get a 2. So the value will be here. Okay. So what is this operation? Very good. It's not a convolution, it's a correlation. I don't know why do people call this as convolution. Ashish, why do you call it as a convolution? No, it's a correlation, isn't it? In convolution, what you do is the filter is there, you turn the filter around and then you multiply. Yeah, that's the difference between convolution and correlation. In correlation, you do not reverse the filter. In convolution, you reverse the filter. So this action should be called as correlation. I don't know why people call it as convolution. Right? Okay. Is this clear? You remember from the last class, in convolution, you reverse the filter and then apply it. And then in correlation, you just apply it as it is. So that's the only subtle difference. So it's a correlation operation, but popularly it is called as convolution. Okay. Little louder, please.
Could you re-explain
How
how is this filter getting horizontal edges?
is this filter? Horizontal edges. Good question. So let me try to explain it once again. Okay, so here we have a horizontal edge, right? Let's look at this window. So what's happening here? And this is like this. So I multiply this with -1, this with -1, this with +1, this with +1. What do I get? -2, right? So I get a non-zero value here. Yeah, this one. I get a -2 here. But if I take, let's say, this window, which is all same values, all are +1, right? What will I get? I will get 0, right? So for the flat surface or for the surface with no change, I get a 0. Now let's look at a vertical edge. So here we have a vertical edge. Oh no, I don't know why my pen is so slow. Okay, so this is a vertical edge now. Can you see it? If I multiply with the filter, what do I get? What do I get? 0, right? It is 1 times -1, 1 times +1. that is 0, and then 0 times minus 1, 0 times plus 1. So ultimately you get a 0. This is this value. Is this clear?
How did you get the last row of the second matrix? 0, 3, or 0?
This row,
Yeah.
you can tell. How do I get this?
Because when you selected 1, 1, 0, 0, it gave minus 2.
Uh-huh.
But it's not in the last row, it's in the second last.
Yes, yes. So,
Padding, so it's 0 padding.
yes, 0 padding. 0 padding means, okay, I want to find what should be the, means is there any edge here or not? How do I find it? So I introduce extra 0 row here. It's called 0 padding, and then I find it. If I don't do 0 padding, then my output size will be smaller than, this is 5 cross 6. Means the input is 5 cross 6. Output will be smaller than 5 cross 6, maybe 4 cross 5 something. But here it is larger than that because of 0 padding. Okay. Okay, so this looks, here it is same thing but shown with the help of images. So basically the matrix, wherever there was a 0, I made it black. Wherever there was a 1, I made it white. So visually it will appear something like this. You can see wherever there is a vertical edge, or you see no change. Wherever there is a horizontal edge, you get large values there, right? Okay, if you take a mod, you'll get better visualization. But anyways, so this is how it looks like. Okay, now I took some synthetic examples. I wrote some letters with my pen and put them here. So you can see, what is the first filter detecting? The first filter. What is this detecting? Horizontal edge. And this one is detecting vertical edge. So you can see in the figure, if I convolve ma or correlate ma with this. So anyways, we'll use convolve because that is the standard nomenclature used. If you convolve ma with this, I will get vertical edges, horizontal edges are highlighted. Like you see black and white, because black is there when so if you come in this direction from top to bottom, wherever white becomes black, or means, okay, in this case let's say white is 1, black is 0. Whenever you go from higher to lower, you get a negative value. Whenever you go from lower to higher, you get a positive value. Negative value is black, positive value is white. Clear? So you're getting two lines here because there are two edges. And in between, when there is plain black, there you don't get anything. Similarly, if you keep coming down, you will again get a positive edge or a negative edge and a positive edge. So that's what is represented by the black and white lines. And so now if you look at this figure, this is detecting the vertical edges. So you see, whenever a vertical edge appears, you get high values of black and white here and here. But along the horizontal edges, you don't get any values. These little bit noise is there because I wrote it with hand. So there were, it is not perfect lines. These are not perfect lines. So wherever you see the pixels are changing, like this kink is there, so it appears here, right? Okay.
How do you decide the size of filter? For example, in the previous case, you used a 2x2.
Good question. So how do I decide the size of the filter? So this filtering which we are discussing now, it comes from the era of signal processing. It does not use machine learning, right? These are handmade filters. So I can choose any size based on my intuition, 3x3 or 5x5, 2x2. But yeah, so it is in your hands what kind of filter you want to design.
Does it really matter?
Yes, for horizontal and vertical edges it might not matter. But for other kinds of edges, let's say you want to detect different orientations, not just vertical and horizontal, let's say slanting orientations, then you will need, it will matter, right? What resolution you can get. Like with a 2x2 filter, how much resolution can you get? Just 2 diagonals, that's it. But with a bigger matrix, you can get more resolution of your orientations, right?
So by the edges divides
darker, one is brighter.
Okay.
Why there is a darker one?
Good question. I just answered this question. Anybody wants to answer? Yes. So if you come from top to bottom, like look at this ma. If you come from top to bottom, so first you will hit a, let's say white is a high value, black is low value. So you hit a negative edge. You go from a high to a low. So you get a negative difference, right? So the negative one is represented by the black.
So good zero is black, so what does negative mean?
Pardon?
Or zero represent the left part.
Okay, so in this figure, 0 is not black. It does automatic scaling. So it represents -1 with black, +1 with white, and 0 with gray. This image. So it is always a good idea to also draw the color map, like which value is mapping to what color. So which I did not do here. So I will be careful next time. Okay, so that's why you get two edges, one for -1, one for +1. And in between there is a gap because it is a flat surface. Okay, so one more point. So when I obtained this figure, this ma sign, I used my pen to write it. But when I imported it into Python, I binarized it to 0 and 1. Otherwise it would be grayscale, means continuous values between 0 to 55. Continuous values would have been there. And then I won't be able to see these edge effects very nicely. So I binarized it with a threshold. So that's why you are able to see the edges very clearly. But if you take real grayscale images, then it won't be this nice. Oh, I think I did not put that image. I had taken one image of the same rows which you saw in the previous figures. And I tried to apply the same filter. This effect is not very well visible for the horizontal or vertical edge filtering. Simply because that is a grayscale image, so there are so many variations. Okay, so what is the essence of our discussion? We are trying to mimic ear detectors or eye detectors. Okay, in this we saw two examples. So better take lessons from them to formulate the space, right? And this is not just true for image and audio. This is true for any domain of signal processing you work with. So recently some of us are working on some problems in physics. They have very different kinds of invariances. They have very different kinds of like what you call as same, what you call as different, right? So there you have to design features to make your learning very efficient. But the basic principle comes from these lessons. How do you design those features? Okay, so what we discussed in this lecture means this continuation from the last lecture. We discussed about space, about detectors, feature extraction, sound features, and today we also saw image features. Okay.